Hi there. Thanks for joining us again. This is Space Nuts, where we talk astronomy and space science and all sorts of other things. And over the last few episodes, we've been doing some specials because Fred's away, gallivanting around Scotland, playing a lot of golf. So we're doing some specials with Jonty Horner, and we're doing part 2 today of astrobiology, a fascinating part of astronomy and space science, one area we get so many questions about. So stand by as we get into that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And back with us again is Jonty Horner, Professor of Astrophysics at the University of Southern Queensland. Jonty, hello.
Afternoon, how are you going?
I'm all right. Can you imagine Fred playing golf? No.
Not sure. I mean, growing up in Yorkshire, the weather wasn't always suited to it, and we were too busy eating gravel anyway, so...
Yeah. Took a moment. I got that. Yes. Used to look clean with the tongues.
Used to have to get up in the morning at 10 o'clock at night, half an hour before I went to bed.
It's just one of the best pieces of comedy ever.
And it's funny because it's true.
Yes. But tell the young people that and they won't believe you. Oh, gosh. It's all flooding back. We've got a lot to talk about, so we better get started. Astrobiology Part 2. Couple of episodes ago, we talked Astrobiology Part 1, surprisingly. Let's just do a quick review.
Yeah, this is a bit like the bit that really annoys you at the start of those multi-episode shows where they say, previously on astrobiology. But this is basically a case of Jonty talks too much, and so therefore we run out of time. I mean, we don't need to sugarcoat that. And it's always the problem when you're talking about something you love and you're passionate about, that the time just flies by. And hopefully it's flying by for the listeners as well, rather than boring them to tears. But, I can't really control that. In the first episode, we talked a fair bit about the fact that we've always wondered whether there's life elsewhere. We talked a bit about the history, in particular things like the ideas of potentially there being life on Mars that led to the Panic Over the War of the Worlds broadcast, and the fact that in the late 1800s, people were that convinced there already was known to be life on Mars, that when a major prize was offered for the detection of life elsewhere, Mars was explicitly excluded because that's too easy. So we've had these ideas for a very long time. But finding evidence of life out there is really, really difficult. We've talked a fair bit about the search for life within the solar system. Places like looking at Mars, looking at Europa, all the icy moons. And we talk about that a lot in the questions that we get week by week as well on the show. And one thing I've always been really interested in and passionate about is the search for life outside the solar system. Given that we've moved into the exoplanet era, and we talked a lot about this in the previous episode as well, we're now in a position where 30 years ago would have seemed impossible. 30 years ago, we'd only just found the first planets around other stars and only just answered that question of whether there are planets at all beyond the solar system. Now we're at a position where we are finding places that theoretically in the future we could search to see whether there's any evidence of life in those planetary systems. And in all honesty, despite some of the hyperbolic media articles that you sometimes see, we haven't yet found a planet that would really look like another Earth, but we're getting there. We're getting closer. We're getting to planets that are more similar to ours in size, at more similar distance from their stars, and we're learning more about them. And it's very feasible then in the next decade or so that we can actually start looking to see whether there's any evidence of life on those planets. Now, that's a little bit separate to looking for signs of communicative alien technological life, which is a search for extraterrestrial intelligence or the search for extraterrestrial artifacts. They're two areas of science that are fascinating, but they're more like a search for a needle in a haystack, where we don't even know if there is life elsewhere, never mind intelligent life. I mean, some people argue whether there's intelligent life on Earth, looking at the news at the minute, but looking for intelligent life that has reached a certain technological level to communicate with us is challenging. It's one of those things, if we don't know what we're looking for, but if we don't look, we'll never find it. But it still led to some really fascinating research. And there's a guy who works with us as part of our Planet Search Consortium, a guy called Jason Wright in the US, who spent some of his time actually thinking about alien megastructures, the kind of things that feature so heavily in some advanced science fiction, like Larry Niven's Ringworld or Dyson Spheres, these enormous structures that you could imagine a civilization building if their technology is as far above ours as ours is from the Stone Age. The idea that you could build something to harness all the material in your planetary system, harness all the energy from your star. Now, many people argue that while that's theoretically possible, it just wouldn't be worth the effort. But what Jason's been looking into is effectively not could people do this, but rather if they did, what would it look like? So it's not really putting any weight on the probability of these things existing, but rather saying, here are things we could imagine that are within the bounds of physical possibility to build, even if they're beyond us technologically. What would they look like to our different kinds of telescopes? What would the signatures be? And that work's really important because if you don't have an idea what these peculiar objects would look like, when you find something unusual, you won't have that thing to reference again to check it out. So both the search for extraterrestrial intelligence and the search for alien artifacts are kind of a separate splinter of astrobiology that are ongoing, that are very precious to us here in Australia, of course. We would have lost the Parkes Radio Telescope under the Liberal government in the 2010s in the previous decade because they wanted to shut it down and demolish it to save money, and it only kept going by a large investment as part of a project to listen for aliens. So 40% of the time on that telescope has been used to search for extraterrestrial intelligence in the form of radio signals, and that has kept one of our incredible pieces of astronomical heritage in Australia, and something incredibly precious and beloved has kept it going and kept it standing despite the worst vagaries of politicians and all those challenges.
Could you argue that we have already created a megastructure around Earth with the number of satellites that are currently in orbit and the so many thousands more that are going to be put up there in the near future?
It certainly feels like that from the inside looking out. I mean, I'm enjoying all the photos people are taking of Comet 2025 R3 Pan-STARRS at the minute, which behind both of us are our attempts. We're showing them off. Andrew's ever so proud from his attempt last night.
My first ever comet.
Fabulous photos that people are getting. But I've seen a lot of them getting photobombed by Starlink satellites. And I'm currently, thanks to learning something new about astrophotography over the last 2 days, I'm going back to images I took of Comet Atlas and Comet Chuchinshan Atlas, which were the great comets of 2024 and 2025, to reprocess those images. But one of my abiding memories of Comet Atlas was I had this incredible view of it on the horizon and took this long series of photos, and every single blooming photo was ruined by a Starlink satellite because I got a Starlink train passing overhead that had recently been launched, all of which went straight through the middle of the comet and rendered all the photos unusable on my only really good clear night. Now I may be able to solve it, but that isn't quite at the megastructure stage yet for me, in that I suspect with the level of technology we've got now or in the near future, that network of satellites around the Earth wouldn't be something we could detect orbiting a planet around another star.
Right.
They're not there yet, but they're the forebears of something that could be. Now, being that they're around a planet rather than a star, their signature would be different. And given that we are very skilled now at broadcasting in one direction rather than many, and that broadcasting directionally rather than broadcasting the boy band, One Direction should be said, broadcasting in a directional sense, we are moving towards the point where we're going to stop shrieking like a screaming infant into the cosmos anyway. So it may be that we're going to go radio silent fairly soon, and satellites like that are going to be part of that journey. But I think they are an indication of how quickly these things can happen. You know, if we were talking a decade ago, we'd have been talking about a couple of thousand satellites orbiting Earth. We're now talking about roughly 50,000, with plans to have more than 1 million within the next decade. It's getting quite terrifying, actually, as much from the atmosphere and climate side of things as anything else. You know, if we have 1 million Starlink satellites in orbit in 5 years or 10 years' time, they have an average lifetime of 5 years, which means we'd have more than 500 per day burning up in the atmosphere. And that's a factor of 100, if not more, times material entering the atmosphere on a daily basis than we get from the background of space stuff falling in. We will be running an experiment in atmospheric science that we've never run before, dumping hundreds of tons of aluminium into the upper atmosphere every day.
Yeah, what's the effect going to be? And that's the $64,000 question, I suppose.
But now the interesting thing there, coming back to the astrobiology, is that might well create a signature in the Earth's atmosphere that would be detectable from observers from around another star. Because one of the ways that we would look for biosignatures, at least early on, would be to look at the light from a star reaching us whilst a given planet is transiting between us and the star, so blocking a bit of that star's light. We can currently do this with giant planets Jupiter-sized, and a fraction of the light from the star passes through the planet's atmosphere, and you get imprinted on the star's light the chemical fingerprint of the constituents of the outer layers of the atmosphere where the light's passed through, in the form of absorption lines. And by studying them, we can work out some of the chemical species that are prevalent there, and even learn a bit about the structure of the atmosphere, the presence of clouds, things like that. Now, when we get to the point where we've got all those satellites burning up in our atmosphere, imagining with the kind of technology that we're looking at developing within the next decade or so, or maybe a little bit longer, imagining being on a nearby star, looking at the sun while the Earth is transiting, you're suddenly introducing a huge spike of aluminium into the absorption in an Earth-like planet's atmosphere. And there is no natural way that I'm aware of that you could get that. So that would not only be a sign of something we're going on, it would be a biosignature of technologically developed life that is not quite so developed as to have learned that pollution is bad.
Maybe that's how we find an intelligent species beyond Earth. They find us first and send us a welcome pack.
Yes. 10 helpful things you can do to fix your problems.
Yes.
Stop burning things up in the atmosphere. Yes.
Yeah, they may have already learned that lesson, but yeah. Okay, so that's where we're at so far. Yeah. Where do we go from here on the astrobiology train?
Well, where we moved to in the latter part of the last astrobiology episode was my argument that you can't just look at a planet and say it's at the right temperature, in the habitable zone, we can look there. It kind of feels a bit like that when you read a lot of stories, that the only consideration that comes into play is how far the planet is from its star. And I think instead it's fairer to say that there are a huge variety of factors that could make one planet more or less suitable for the development of life and therefore for the observability of life on planets around other stars. And therefore, given that the observations to find life are going to be overwhelmingly the hardest we've ever had to carry out, we'll have hundreds, if not thousands, of targets to choose from, but we'll only be able to look at a tiny handful of them in detail at first. So we need to be very careful about where we look. The proximity of the planet and its host star to the sun will be important because the closer the star is to us, the more light we get for a given brightness of star, and also the more widely separated on the sky a star and planet will be for a given orbital distance between them. Closer they are, the more widely separated they are. And while people listening can't see this, I'm at the minute putting fingers up at the side of my eyes to Andrew and then moving them towards the camera. Fingers are the same distance apart, but they get wider and wider apart on the screen as they get closer.
Yeah.
So there are clear reasons that we will look at stars that are nearer to us rather than further away. But beyond that, I think it's really important to consider all the different things that could factor in to make a given planet more suitable or less suitable for the development of life, and view them as like sliders on a mixing board in a sound studio, where you can fine-tune things to see which gets the best sound, which gets the best score. You can rank your targets, and you can start with the most promising ones, because with limited resources, you don't just want to do an unbiased survey, you want to instead maximize your chances of a positive result. Now, we're heavily biased. We only know of one kind of life, and that's Earth life. So we are very biased towards looking for places that could support life like Earth life, because that's the only kind of life we do know exists. That'll factor into it as well. But in the previous episode, towards the end, we talked about the way in which the location in the galaxy could potentially influence this, with the caveat, of course, that we're going to be looking at everything nearby. So whilst that's interesting scientifically, it's not that relevant. And then we also talked about the way that the nature of the stars that the planet orbits can influence things. And not just from the point of view of is the star stable or single, but down to more subtle things like the fact that stars brighten over time. So just because a planet is in the habitable zone now doesn't mean it's been in that zone for long enough for life to become well established. So we talked about all that. Where we finished up, though, we didn't get to my own personal favourite parts of the science and the stuff I'm more directly involved with, which are the more local influences on the planet. That is, the influence of the planetary system in which that planet moves, all the other planets and all the debris therein, but also the impact of the planet itself, what it's made of, how it behaves. And there's a lot of subtlety in that when I prepared with my old mentor, Professor Barry Jones, this review article on this 16 years ago now, we dug into, and it highlighted to me how none of these questions can be answered from people within a single research silo at all. You need researchers from all different disciplines of human experience, from the sciences, the biological sciences, physical sciences, geosciences, chemistry, and astronomers all to come together. You probably also need philosophers and archaeologists to come into the discussion to talk about how we look and why we look and what we look for. And that's particularly true when we start moving from simple life to life that could talk back to us. And a very dear friend of mine in Australia, who Fred probably knows very well as well, is Professor Alice Gorman down at Adelaide, who's a space archaeologist and has given some of the most astonishing and mind-blowing talks I've ever seen from the point of view of someone who is trained in archaeology, looking at the record of human spaceflight and what we should do to preserve artifacts like the Apollo landing site for future generations, how we should consider that.
Mm. I absolutely agree, because it was probably one of the greatest achievements in human history, if not the greatest achievement in human history. I mean, inventing the wheel probably would have been a pretty cool thing too, but I don't know where that happened or when, and they'd never would have thought to commemorate it. But it is something that should, when we eventually have permanent residence on the moon, at least need to put a cyclone fence around it just for the time being until we can build a proper, structure to protect it.
Probably a good place to have a rabbit-proof fence, because that'll do the job.
You know that rabbits will ultimately be on the moon. They tend to be everywhere else.
One of the greatest conference talks I ever witnessed actually was a talk by Alice talking about archaeology, and it was from the education and biases point of view. And I know this is already a bit off topic, but it's a story I think really well worth repeating. Alice is an archaeologist, and so she teaches archaeology students. And she gave this talk about how she took a group of her final year students to this site in fairly regional New South Wales for a 2-day dig. Basically, go out there, dig, and come back to me with what you find and tell me about the story of the site. And after 2 days, all these young students came back and said, look, we didn't really find much. We found a few Aboriginal artifacts, and that's kind of interesting. But all we found was a load of rubbish. We found all these blooming cable ties and bits of plastic that are polluting the site. What she then went on to do was, the whole point was that the cable ties were actually the archaeology that she was interested in. So she went on and said in the talk that this was an old decommissioned listening station that had been built, I think, in like the late 1940s, post-World War II, and operated into maybe the late 60s, early 70s before being demolished and removed. But by looking at the cable ties, where they'd been identified, and knowing a little bit about how cable ties and cable tie technology changed over the years, you could not only map out exactly where all the buildings had been and where the wire runs had been and get the structure of this long vanished building, you could also work out which bits were built when. And the whole importance here was partly that whole thing of one man's trash is another man's treasure, but it's also how, as a scientist and a researcher, you will miss things and you'll make mistakes because of your own personal biases that are quite often unconscious. And in this case, for these students who've been studying archaeology, their unconscious bias was that anything modern is not archaeology. That's rubbish in the way of good archaeology. And so they totally miss the point. And it's a fabulous learning thing. It's why, as scientists, we use statistics so much. I know there's all this stuff about you can show anything with statistics, damn lies and statistics, all the rest of it. But fundamentally, the reason that we use statistics as a tool is because we as humans are biased. We've got this incredible evolutionary ability to see patterns when they're barely there, but we also have a very strong ability to see patterns that we expect to see when those patterns aren't actually there. And that's certainly true of the canals on Mars. Giovanni Schiaparelli saw these canals, these channels on Mars, which I think the best explanation is that Mars was really bright. He had a big telescope and he was actually seeing the projection of his own capillaries in his eye, like I'm going to see tomorrow when I get my eye test at the opticians and they do the bright light thing. Yeah. But all these other observers with less good eyes and less good telescopes suddenly started seeing the canals. And it's this whole thing of when you're really straining at the limits of your vision, you see what you think you're going to see, not what there actually is. And that's true with our data. Therefore, you use statistics to give you a feel for whether what you're seeing is significant or not, or whether it exists in the first place. And that's a way of us combating those biases. Now, that wasn't available in that way to the archaeology students who thought that cable ties were rubbish, but it was a fabulous reminder of how we really need to be aware not only of the explicit biases, which are the things we choose to do. You know, like if they're doing a survey of people on hair loss and they say, we interviewed men between 18 and 30, that's clearly biased to be for men between 18 and 30, not for men of our age. For example, That's an explicit bias. It's one that's a conscious choice. Implicit biases are the sneaky ones where you don't realize you're making them. And that's why I've made it so clear up front here that we can imagine all kinds of life. Science fiction does it wonderfully. But our implicit bias is that when we talk about the search for life, at least in the very short term, we're actually looking for life like us, not you and I, but life like Earth life, based on a planet with oceans living on the surface, modifying the atmosphere, because that's the one kind of life we know exists, but also because that's the one kind of life we could probably identify with our observations. Life beneath the ice on Europa is fascinating, but we can't see it in the solar system. We wouldn't have a prayer if Europa was found orbiting another star because the ice is in the way. Yeah. Life on a surface that modifies an atmosphere is at least something we theoretically could detect. So that's making the implicit explicit.
Gotcha. All right. We're going to take a breath and get back to Astrobiology Part 2 on Space Nuts. Let's take a little break from the show to tell you about online security with our sponsor, NordVPN. Now, you probably heard us talk about NordVPN before. They've been with us for a long time and we really appreciate it. But there's a good reason for that. It's something that we actually use. Me personally, especially when traveling. In fact, last year when Judy and I were overseas, we ran into a situation where some of our everyday online apps on our phones just wouldn't work. Our banking app, for example. And that was crucial because we were actually selling a house while we were on a cruise ship. Yeah, don't ask. It was a strange situation, but we needed access to our bank accounts to make all that happen, and NordVPN was there for us. I even got to watch sport back home, even though we were geo-fenced out of the district because we were over in the Mediterranean or somewhere like that. So with NordVPN, I was able to log in and watch the football back home. It lets you securely connect through servers in your home country so your apps will behave like you're at home. But it's not just about access, it's about protection. NordVPN encrypts your internet traffic. So whether you're on public Wi-Fi or on your home network, your data is shielded from hackers and trackers and unwanted snooping. It also has a built-in threat protection system, which can block malicious websites and annoying ads and even prevent malware downloads before they happen. And setting it up, very easy. One click and you're protected across multiple devices, up to 6 devices with one service. Right now, if you'd like to take advantage of a special Space Nuts listener offer, you can head to this URL for more information, nordvpn.com/spacenuts to get 4 extra months free plus a 30-day money-back guarantee. They can't make a much better offer than that, can they? That's nordvpn.com/spacenuts, and don't forget to use the code word spacenuts. Secure your connection wherever you are in the world or the universe with NordVPN, our sponsor.
3, 2, 1.
Space Nuts.
And you're with Andrew Dunkley and Professor Jonty Horner. Okay, what next, Jonty, in this search for extraterrestrial life?
Well, I think we come back to moving away from the diversions of archaeology and stuff to the factors that could make a planet more or less suitable as a target. And like I say, we talked about the galaxy, we talked about the stars. To me, as a person who comes originally from a solar system background and is particularly fascinated with comets and asteroids and stuff like that, there are a lot of factors that have been proposed that relate to the interaction of planets and the interaction with the debris that's around that could render planets more or less suitable as targets. Now, one example of this is the stability of orbits. There are a variety of different models of the solar system's youth, some of which suggest that there were periods of chaotic instability where the planet's orbits got stirred up, planets maybe even swapped orbits. Now, this is the kind of thing we can model, and when we discover planetary systems, we can take the planets that we think are there and put them into computer software to run their orbits forward and back in time to see how they behave. And that's actually part of my day-to-day work. That's the technology I use, and that's the tools I've used in the past to kill planetary systems that people thought were there, because I ran simulations and showed they're simply not stable on very short timescales. But on longer timescales, these kind of perturbations can have a significant impact on the orbits of planets. You can get significant shifts over time. You can get encounters and stirring up, which means sometimes that a planet will be on an orbit now that is not the orbit it's occupied in the past. And those are things that we could probably tease out from the simulation kind of work that I do. And obviously a planet that is now in the habitable zone, but that was previously well outside it, would not be a good place to look. Even though it looks good now, it's not great. It's like, I guess, you've got two petri dishes in front of you that you could look at for life, but you can tell that one of them's been absolutely melted in a fire. It's at room temperature now, but that doesn't mean it always has been. That same kind of idea. So that on a coarse scale has an effect, but there's a subtler version of that I've done a little bit of work on in the past, and I've got a PhD student working with me at the minute who's going to look into this a lot more, a wonderful student called habitability. It's the idea of the Milankovitch cycles. Now, on Earth, we look at climate change in the short term as being a big problem because it's a very rapid change that is being caused by human action. But on much longer timescales, the climate of Earth is periodically variable. We've had ice ages and interglacial periods for the last 2 or 3 million years, which are the direct result of the subtle nudges and tweaks on the Earth from all the other objects in the solar system, primarily the other planets, and not mainly Jupiter, to be honest, but most of the planets contribute. These are called the Milankovitch cycles. They have a number of effects. Firstly, the Earth on its axis precesses. It wobbles with a period of about 23,000 years. So our polar axis, which is tilted by currently 23.5 degrees to the plane of our orbit, wobbles around like a kid's wobbly spinning toy coming to a stop. It precesses, wobbles around a bit like the thing in Inception about to fall over. You see this precession. That's a precession of the equinoxes. That's why your horoscopes are wrong. Well, it's one of the many reasons that your horoscopes are wrong, but it's particularly why your horoscopes are out by one full calendar month, because the horoscopes are based on where the sun was in the sky at that date 2,000 years ago, and the axis of the Earth has wobbled round, so it's now one constellation round. So when the sun is in Aries, according to your horoscope, it's actually now in Pisces, all because of the wobble. That wobble takes 23,000 years to complete. That means that the direction that the Earth is pointing changes over time, essentially. Yeah. Added to that, you've got a very slight wobble up and down where the tilt of our axis, which is currently 23.5 degrees, changes from about 22 to 24 degrees, rocking back and forward. So that causes the size of the Arctic and Antarctic circles to grow and shrink very slightly. On top of all that, you've then got the Earth's orbit around the sun flexing and tilting. Its shape becomes more circular and more elongated, more eccentric, with a longer period, I think about 100,000 years, something like that. Our orbit, compared to the orbits of Jupiter and Saturn, tilts a little bit up and down. The inclination changes, which adds to the change of the tilt in our spin axis a little bit. We also have the Earth's orbit precessing around in just the same way our poles do, and that's a little bit harder to visualize. But what that means is that the direction, if you drew a line from the sun through the Earth and out into space at the point the Earth was at perihelion, closest to the sun, that direction will gradually move round over time, doing a full lap with a period of several tens of thousands of years. So our perihelion position precesses as well. All of that combined means that, on average, the amount of energy reaching the Earth's polar regions averaged over a given year varies with time. Sometimes the poles get a bit more energy and the ice sheets retreat. Sometimes they get a bit less energy and the ice sheets come back towards the equator again. Now, there's a lot of complex feedback from the Earth because ice is more reflective than water or land. So when ice is growing, it has a tendency to keep growing. And when it's shrinking, that has a tendency to run away as well. So you've got all these different feedbacks. But what that means is that on the Earth, we've got these periodic variations in the amount of energy at the poles, which lead to periodic glaciations and interglacial periods. That's the Milankovitch cycles. It means that on timescales of tens of thousands of years, our climate is relatively changeable. What would happen if the planets were on different orbits? Or if you were in a planetary system with a totally different architecture? The result would be very different Milankovitch cycles. You'd have different periods, and you'd also have different amplitudes. You could imagine scenarios where instead of our Earth rocking a little bit from 22 to 24 degrees and back with its polar axis, it could be like Mars, whose spin axis varies chaotically, can even tip over on its side. You could have systems where there's barely any change whatsoever. You've got this full gamut. Now, the beauty is, again, we've got the tools to test this. We can run the kind of computational simulations that I've spent my career doing and model the orbits of a planet over time under the influence of all the other planets. And I did a lot of simulations of this between 2012 and 2020 and kept coming back to the idea but never got around to publishing it until we got to 2020, where I published it with Stephen Kane from University of California, Riverside, Pam Vavort, who was his PhD student at the time, a couple of other people, where we said, what is the influence of Jupiter on our Milankovitch cycles? What would happen if you moved Jupiter closer to the Sun or further away? If you made Jupiter's orbit more eccentric or less eccentric? How would that change the period and amplitude of the Earth's Milankovitch cycles? Did the test, and in many cases, moving Jupiter destroyed the solar system, which meant the Earth wouldn't be here, which was kind of fun but not very helpful. But for the versions of the solar system where the Earth was not removed, we got to see the range, the variety of Milankovitch cycles we would have from moving Jupiter in a bit closer or moving it a bit further away. And for those really interested, we moved Jupiter in as far as 3 AU from the Sun, out as far as 7 AU from the Sun, where 5 AU is about where it is at the minute, 5.2. What we found, which is quite surprising, is that the Earth's Milankovitch cycles are neither unusually big or unusually small. They're somewhere in the middle, which is a bit of an argument against a hypothesis called the rare Earth hypothesis. This idea has been around for about 20, 25, 30 years, and I've never really liked it. It's the idea that life on Earth is such a remarkable, incredible fluke that we will never find life elsewhere. And the authors put forward all these peculiarities about the Earth and argue that without them, we would not be here. And it's a bit of a philosophical thing, but I think it's very dangerous to look at somewhere that has life and say, this place has all these unusual things and they are therefore required for life, because we've never found life elsewhere. A good example is the presence of a large moon, and we'll talk about this a bit more later on. We have life on Earth and we have a big moon, so it's natural to think you need a big moon to have life. But we won't know that until we find life elsewhere. But that led to this argument of rare Earth. Life will be uncommon in the universe. If rare Earth were true, then when you look at something like the Milankovitch cycles, you would expect our Earth to be unusual in some way, to have conditions that favour life over your typical system. And we simply don't find that. Our Milankovitch cycles are fairly run-of-the-mill. They're not big, they're not small, they're not fast, they're not slow. They're somewhere in the middle. Now, where Pam went with that, Pam Vavort, was she then took the output of that and ran it into climate modelling software, which was fabulous. And she published that work with us in 2022, where she was able to link the Milankovitch cycles we predicted if you moved Jupiter around with the amplitude and frequency of the ice ages we'd get. And it was really interesting because it turned out that when you factor in some of the feedback mechanisms that are in climate modelling, you actually could change the Earth's Milankovitch cycles a little bit and get very drastically different ice ages, much more frequent and shallower, or much less frequent and deeper, just by small changes. Now, it's all fascinating just from the solar system point of view, but what we're really doing is we're putting down tools that when we find planets that could be suitable, we can do these same tests. We can look at them and say, we're thinking that you might be a good target for life. Let's see what your Milankovitch cycles are like. Let's see how stable your climate is. And if we find somewhere that flops between snowball Earth and a hothouse every 10 years, or that has incredibly long snowball Earth periods followed by short periods of temperate climate, even though everything else looks good, that's probably not as suitable for life as somewhere that is temperate all the time. So we can use that as a bit of a filter. And that's where The new PhD student we've got, Amber Tilley, comes in. Amber's going to be doing the same kind of work moving it forward, where she's going to be looking at a whole slew of different parameters to see how the Milankovitch cycles change as you vary things. She's both going to look at what would happen if the Earth was a bit more massive or less massive? How would that change things because of the feedback? You make Earth more massive, it interacts more with other things, stirs them up, you get a feedback there. She's also going to look, working with colleagues of ours overseas, at models of planet formation that form planetary systems similar to the solar system as theoretical data and say, what would the Milankovitch cycles be like in this hypothetical system? So it's not just a purely hypothetical question, it's something we can actually dig into and we can test. And I think that's fundamental to science. It's no good just arguing something, you want to be able to test it.
Yeah, I suppose what you're suggesting is that by mucking around with what we know and making slight alterations, it gives you an idea of what to look for going forward in identifying potential targets.
Absolutely. And it's good because one of the reasons that you'd want to use the Earth is because we've got a ground truth. You can run the Earth with the current solar system parameters and put them into a climate model and you should get what we see. So we can ground truth it, which is really, really important. And that is, I think, one of the main, most obvious ways where even in a dynamically stable system, a system that isn't tearing itself apart, interaction between planets could have a significant impact on habitability. And we want to look into it. It's really, really fascinating.
Indeed it is. All right. We are talking astrobiology on this special episode of Space Nuts with Professor Jonty Horner. Back in a tick.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Jonty, I thought we might just start off this final segment with a question from the audience. It's funny because this question's come in before any of these astrobiology episodes have been released. And yet it's exactly what we've been talking about. This comes from Chris.
Hi, I'm Chris from Exmouth in the UK. I'd just like to ask, given that interstellar travel to distant solar systems is likely to remain impractical for humans, do you think a more realistic long-term strategy would be to seed the galaxy with the basic building blocks of life? For example, sending autonomous probes carrying microbes or prebiotic material that could eventually take hold on suitable planets, even if that process takes thousands or millions of years. Thanks.
There's a thought from Chris. He's probably suggesting, could we seed other planets? Would that be the way to go? And autonomous vehicles. I think last time we talked about this a couple of episodes ago, you suggested it's beyond us to actually send a human mission to another world to investigate life, but we could go the way of autonomous vehicles. But for the major distances, like the impossible distances, we would have to come up with equipment in the future that could do it from a stable environment nearby. I don't know how you want to tackle that question.
There's a fair bit to it. And I mean, it reminds me of the wonderful Bobbyverse books that I've quite enjoyed, the story of the self-intelligent von Neumann probes, which are easy listening and work very well as audiobooks. It's a challenging one. So we could do this. It would be feasible. The question would become whether it's ethical and right.
Yes.
And that's a really challenging one. Now, there is something that costs research missions a vast amount of money called planetary protection. And it's the idea that if we're sending a spacecraft that has a possibility of touching down on a place where we are currently interested in looking for life, where there could be life, such as Mars, such as Europa, Ganymede, Titan around Saturn, we don't want to take life with us because you don't want to find life on Mars only to discover it's what you took with you. And also we don't want to pollute or contaminate those environments. So there's a huge amount of effort and expense goes into extreme sterilization of spacecraft to kind of prevent exactly the hypothesis being discussed here. At the same time, that idea of populating the galaxy with simple life that could one day grow to resemble us or something else has cropped a few times in science fiction. I believe that was how Star Trek got around the fact that all of their humanoid species looked like people with makeup on,
Yes.
which of course is a budgetary issue and a special effects issue. But they had an episode where people found the Founders, which were an ancient alien humanoid race that seeded the galaxy, and billions of years later all these different planets had grown humanoids that looked like them. And oh well, convenient, job done, stop asking us that question now please, effectively. It is something we could do, and the timescales would be immense. It's also something that, in all honesty, has already happened. There's this idea called panspermia, which is the idea that life could be transferred through space from planet to planet, carried by debris from impacts. And talking 30 or 40 years ago, it was viewed as very much crank science, not feasible. But every experiment that people have ever done suggests that it could work. And I've even had a PhD student just submit his thesis, Greg Davis, who has been looking at this from the point of view of the viability of bacteria transferred from Earth to Mars or Mars to Earth in the radiation environment in the solar system, and it seems to work. Now, to me, the fact that biological material from Earth will have rained down on Mars and Europa and Ganymede and everywhere else for the last 4 billion years probably means that we're being a bit overcautious with our planet protection efforts, because we're trying not to take something there when it's already there. It's already been delivered. The other thing is that anything we take with us to a place that has an incredibly, incredibly different environment, if there is life there already, that life should hugely outcompete anything we take with us because it's better adapted for that environment. And that would be one of the challenges with this, is sending stuff out. It'd have to be lucky to get exactly the right environment to grow. But with the amount of real estate we've got out there, it could happen. People have, even in some more extreme sci-fi, suggested kind of this type of approach as a way to begin terraforming planets ahead of human arrival. This idea that you could send generation ships, which have to go slowly because they're really big and carry a lot of people, but you could send faster moving, smaller things first to start working on the biosphere of a planet to make it so that when we get there, that planet is a suitable home. So there's a lot of ways it could be taken. I think to do it in the near future in an official, organized way would require a significant shift in global morality in the way we think about other habitats. If we found that Mars absolutely has no life, and possibly that it never had life, which I think is probably unlikely, then I could see people arguing then for terraforming. Similarly, people have argued about, I think Carl Sagan suggested this, creating engineered bacteria that could float in the clouds of Venus and precipitate out the carbon to eventually make Venus a more habitable planet on long timescales. The idea of terraforming these worlds is real, but I think it would require either a state to go its own way, because as we know, once things are up in space, ain't nobody going to stop you, as was the case with the Israeli spacecraft that spattered Tamigards, water bears over the moon to show that they could, which was so dumb it's untrue. Yep, there are water bears on the moon, probably desiccated and dried up, but they can come back from that. We know that. So you could have a nation just decide to do it anyway. At the end of the day, if a random government decided to send a spacecraft to Mars within a capsule inside laden with biological bacterial life to spurt out on the surface, no way we could stop them. And once it's done, it's done. But I think the block to the question is not actually a scientific one, it's an ethical one, and it's about how we choose to interact with the galaxy going forward, and particularly our local environment, that'll determine at what stage we do that, if we ever do. So it's a really good question.
It is. Thanks for the question, Chris. Chris, you might be interested to look up the BBC radio science fiction comedy called Paradise Lost in Space. Have you heard of this one? It's so funny. It's about two blokes who get ejected from a spaceship by an exploding toilet or something, and they end up on a world that's occupied by an intelligent but very naive species. So basically what they do is they try to pass on their Earth knowledge and intelligence to these people and ultimately destroy the planet.
As it is perfect reflection.
It is brilliant. It's very funny.
Yeah.
Yeah. It's funny stuff. So, yeah, it's called Paradise Lost in Space. I only remember it because we ran it as a series on the ABC some years ago, and it got a fabulous response. And I sat there in the studio while we were running it, and I just cackled as to, because I could imagine that's what we might do, not on purpose, but yeah. And it's what you say, it's the ethics of sending like our junk to other places that are already occupied. Yeah. We're running out of time, I suppose, but how do you want to wind this up? How do you there's so much to talk about. It could go on for hours, I know.
More to talk about. I think I'll carry on until you kind of get the hook and pull me off about the different things that influence planets' habitability, because we've talked about Milankovitch cycles. We also have, as the influence of the planetary system, impactors, just as the dinosaurs. They had a very bad day. And there has historically been this idea that ties into the rare earth thing that Jupiter is our friend and savior. And without Jupiter, we'd be hit by asteroids more often and we wouldn't be here. And therefore, life is rare in the universe. Idea basically that Jupiter is our bestest friend. And it's honestly a lot of codswallop. And it's both one of my favourite bits of research I ever did and probably one of the biggest bugbears of my career is that I did work again with Barry Jones starting 20 years ago for a few years, that resulted in a series of papers called Jupiter Friend or Foe. And we did simulations to test the role of Jupiter in protecting us from impacts or not. And it turns out that Jupiter is not a shield at all. If you took Jupiter away, Earth would be hit less often. If, however, you replace Jupiter with a planet the mass of Saturn, Earth would be hit more often than we are today. And with Jupiter the mass it currently is, we'd be hit more than if it wasn't there, but less than if we put Saturn there. All down to the subtleties of how gravity all works. And so basically, if you replace Jupiter with Saturn, it's like the anti-Goldilocks case where you've laced a porridge with strychnine. But the reality is that Jupiter's role is complicated. Best illustrated by Comet Lexell in 1770, which I always love. Comet Lexell was a great comet. It was very bright in our sky, discovered by Charles Messier on, I think, 1st of June, 1770. Quickly got as bright as the brightest stars in the sky, but looked unusual. It was very big and fuzzy, and it moved unusually rapidly across the sky at its quickest, covering 42 degrees in a single hour. When they worked out the orbit of this thing, they found, A, that it had come very close to the Earth. It passed within 2 million kilometres, which is the closest approach of a large comet in historical times. It also was moving on an orbit that was just less than 6 years in period. Big, bright comet going around every 6 years. Why on earth had we not seen it before? Why had we not seen it in 1764 or 1758? Well, when they worked out the orbit and ran it back in time, and this was hard at the time because they didn't have mechanical computers, they had human computers who sat there and did calculations with abaci and slide rules and all the rest of it. They found that 3 years before it nearly hit the Earth, it was very close to Jupiter. And in fact, prior to that, it had been moving on an orbit that came nowhere near the Earth, that was probably hundreds or thousands of years in period. And it was flying in to come nowhere near the inner solar system when it had this close encounter with Jupiter that trapped it and threw it at the Earth and captured it onto this 6-year-long Jupiter family comet orbit. So Jupiter took something that was coming nowhere near us and threw it at us. We don't see the comet anymore because 2 times 6 years is 12 years, and Jupiter takes 12 years to go around the sun. So the comet did 2 laps in the time Jupiter took to take 1. And when the comet got back out there again 12 years after the first encounter, Jupiter was there, grabbed hold of it and threw it away again, never to return. So in just this 12-year period, Jupiter threw something at us and then cleaned up after itself. And whether Jupiter's more of a shield or more of a threat is down to the balance of those two effects. And what we found in our simulations is, to be honest, with Jupiter, we get hit more than we would do if it wasn't there. That takes away the idea that it's our protector. It takes away the idea that you need a shield to shield a planet to prevent life from being wiped out. Another nail in the coffin of rare earth. And it bugs me a bit that so many documentaries still trot out this trite idea that Jupiter shields us from impacts, and it's wonderful, because I disproved that 20 years ago. It's much more complicated. But even that idea gets complicated because obviously we don't want to have the Earth punishingly pummeled because we'd be wiped out. But where the Earth formed in the solar system, it probably formed dry. We formed interior to the location of the ice line, so there wasn't any available solid water. The water was all gas. So how the Earth got its water was a long outstanding problem, exacerbated by the fact that towards the end of our planet's formation, we got smashed into by an object the size of Mars, which stripped off a lot of the Earth's core and mantle and would have desiccated our planet because the water would have been in the core and mantle, in the crust and mantle, up near the surface.
Yeah.
So where did the water come from? And Earth is actually a remarkably dry planet, particularly at the moment in Queensland. The idea
And
is,
down here.
the idea is that our water, at least in significant part, was delivered from further out by impacts in what is often described as a late veneer. That's really interesting, because that's a stochastic process. It's random. It's driven by the orbits of the planets and the cleanup phase of solar system formation. So different planetary systems will give planets with different amounts of water. But it's also indicating that you actually don't want too much shielding. You need impacts. Because if the Earth had never had the impacts, we'd have never got enough water for life to develop and thrive. On top of that, if the Earth didn't have enough impacts, the dinosaurs would never have been wiped out. And maybe you and I would be reptiles. Or maybe we'd be here, So there's a whole aspect of that. Now, again, those simulations I did, we can rerun through the planetary systems. We can find the debris belts in those systems. We can find the planets. So we can model their impact rates. And I'd argue that we want to look somewhere that doesn't have too many impacts, but also doesn't have too few, because each of those could pose problems. That is a really big part of the story, and it feeds into the last point, really, which is the planet itself, and a little bit tied to the large moon. So our Earth, it has been suggested again by the rare Earth crowd that the large moon we have stabilizes our axis and has kept the Earth habitable, so therefore you need a giant satellite. But simulations by Dave Waltham, who's a guy I know very well in the UK, looked into this, and what he found was that you could take the moon away, and the Earth's axis would still be fairly stable. It still wobbled between about 22 and 24 degrees, maybe a little bit more. But quirkily, if you made the moon just 12 kilometers larger in diameter, it would make the Earth's axis unstable and chaotic. So if the moon was only slightly larger, we would not be here. The other reason that a large moon has been suggested is that it drives bigger tides. And one of the common arguments for how life first got going and for how life moved out of the oceans in both cases is to do with the large tidal intertidal areas that we have, where at low tide it's dry and at high tide it's underwater. And the idea is that without the moon, those areas would be smaller and life would have had less chance to get going. I don't really buy that, because if you took the moon away, the tides the sun raises would still be half the size, so you'd still have substantial tides. But these are all the kind of questions people ask before you get to the planet itself. And the planet itself is where my head really hurt. Now, I'm not a geophysicist at all, so a lot of this was new to me. Now, we talked a little bit about the hydration. You can imagine anything from desert worlds to worlds with hundreds of kilometers depth of ocean. Now, if the ocean's too deep, the planet is probably habitable but not detectably habitable, because the life will be at the bottom of the ocean where the nutrients are being introduced by volcanism. But an ocean deeper than a few tens of kilometers is thought to become stagnant, and so it doesn't mix things up to the surface. So you don't want to look at water worlds that are ocean for hundreds or thousands of kilometers depth, but equally you want to have some mix of ocean and continent to allow all the carbon cycles and weathering to happen, to allow life to engage with the atmosphere. So that's a bit of a sweet spot there. But what I didn't realize was how critical water has been to the maintenance of our atmosphere and thereby our climate, against the vagaries of the solar wind and against the vagaries of plate tectonics. Now, compare the Earth and Mars, and the Earth is warm and wet. We've got a lovely thick atmosphere, and we've not really lost much for our atmosphere. We've got the ozone layer, which protects us to some degree from UV radiation. We've got a temperature inversion about 10 kilometers up in the atmosphere that traps water below that level. If water gets above that level, it freezes and falls back down. So the water can't get high enough to be ionized and split hydrogen and helium and lost. Mars doesn't have that. Mars doesn't have much of a magnetic field, whereas the Earth does. And the magnetic field protects the atmosphere from being stripped away from the outside in. Mars doesn't have plate tectonics, but we do. And plate tectonics prevents the atmosphere from being precipitated out onto the surface through chemistry and trapped there, because plate tectonics recycles the crust. So anything that chemically gets weathered onto Earth's surface gets put back into the atmosphere through volcanoes. So Mars and Earth probably started out looking very similar and are now very, very different. And so the nature of the planet itself is going to be a real important factor, and plate tectonics looks like it's going to be fairly key. Plate tectonics is a mechanism by which you stop the atmosphere getting precipitated out and frozen in onto the surface, which is a big part of what's happened on Mars because of that recycling effect. But it also turns out that plate tectonics is key in ensuring the magnetic field is retained. And this is a bit that really hurt my head, because I'm not a geophysicist. Seems that on the Earth, if the Earth didn't have plate tectonics, we'd probably have lost most of our magnetic field, like Mars and like Venus. What's happening is that the magnetic field is driven by convection currents in the outer mantle, like when you see water boiling in a kettle, overturn, motion of molten metal, rising and falling. That convection can only happen if you've got a big temperature difference between the bottom and the top of the outer core. In order to get that temperature difference, you need to be able to very effectively cool the top of the outer core, because otherwise it'd warm up so much convection would stop, because you don't have enough temperature difference. The way the outer core is cooled is by convection in the mantle that takes the heat away from the top of the outer core and brings it to the surface. We've got these huge convection cells in the mantle that transfer heat very quickly, allowing you to cool the outer core's top to get this big temperature difference that allows the motion that drives the magnetic field. That motion is also what drives plate tectonics. Now, the quirky thing that came out of all of this when I was reading about it is that if you run simulations of the motion of the Earth's mantle and the crust, and the Earth is dry, the Earth is too small to sustain plate tectonics because the mantle is too stiff. If you have water and you mix water into the mantle, you lubricate it, you allow convection in the mantle, which allows plate tectonics, which allows you to recycle the surface. But that plate tectonics also allows you to cool the outer core to maintain the magnetic field, allowing you to have that magnetic shield that protects your planet from the atmosphere being whittled away from the outside in by the solar wind.
Wow.
It seems that the story of plate tectonics, the Earth's magnetic field, and the atmosphere being retained is all tied together by water, which brings us back to that delivery question. If the Earth had not got that veneer of water, would plate tectonics still happen? There's even a suggestion, and this was fabulous work by people working with the great Craig O'Neill, a great Australian scientist who does earthquakes and plate tectonics modelling in an astrobiology sense, that says the Earth's plate tectonics are really hard to get started. If you run models of the Earth without plate tectonics, with the young Earth, with how hot it was, plate tectonics don't just happen. However, if you introduce impacts from big asteroids, like the things you got at the end of planet formation, those can dump enough energy in terms of a downward pulse to push magma up somewhere else to trigger a convection cell that then becomes self-sustaining. So it's quite possible that the same impact regime that led to the delivery of water, that led in the extreme case to the formation of the moon, also triggered plate tectonics. And by triggering plate tectonics and delivering water to the mantle, allowed the Earth to become the planet it is today to allow life to thrive. Now, there's far, far more that you could look into about the planets themselves. I'm not, like, say, a geophysicist, but the interplay of these things is fascinating, and it's a real reminder of that multidisciplinary thing. You can't do it all if you're just an astronomer. You need everybody from all different disciplines to come together so we can figure out what factors are and aren't important, so that when we find another 1,000, another 10,000, another 100,000 planets, we can pick the best targets to search for life upon them. And that was the motivation, and it just blew my mind when I got to that final part, just how much complexity there is in the interplay between the atmosphere, the climate, the plate tectonics, the oceans, that are so variable and so chaotic. What does that mean? How can we learn from that? Well, that's what we'll learn when we look at planets around other stars, but at least this gives us a bit of a starting point, I think.
Yeah, I see what you're saying. So it's like the popular press saying, well, we found a rocky planet in the Goldilocks zone.
Whee!
And it probably has water. So, it's got to have life. There's so much more than that.
Oh, yeah.
It's...
even the probably have water is a leap. Because, if we'd not had water added after the moon-forming impact, the Earth would be a desert.
And we wouldn't probably exist at all.
Absolutely.
Yeah, fascinating stuff. Jonty, we'll leave it there, but it's just such a fascinating topic. But what goes into the future identification of potential targets is so much more than most people would have considered. So thank you very much. Really appreciate it.
It's an absolute pleasure, and thanks for letting me rant on my topics of choice for a change. Like I said, it would be helpful. I'm sure your listeners will give feedback on this, but I know we've done something different. I really do. I am aware of the fact that these are not your typical episodes, and that may be different for people. So I appreciate the opportunity to do this. But if people have enjoyed it or didn't, it'd probably be worth letting Andrew and Fred know once I'm gone. Won't hurt my feelings, don't worry about it, because if it's something you've enjoyed, there's possibilities to do things like this again in future. If it isn't, we tried it and it didn't work, and that's entirely fine too. So hopefully it was fun, hopefully it was educational, and I won't be too hurt if nobody enjoyed it.
I'm pretty sure they did, Jonty, and we really appreciate your time. And we've got one more episode to do with you. It's a Q&A episode, and we're talking about, we haven't nailed it down yet, but we're talking about doing an astrophotography special.
Yes.
Because we do get a lot of questions about astrophotography, so that'd be worth getting into as well.
Yeah, I've got a couple of good friends who are award-winning astrophotographers who we're going to try and rope into that. So watch this space. Is what I'd say.
Yes, fingers crossed we can nail that one down. Jonty, thanks so much. We'll see you real soon.
It's a pleasure. Thank you for having me.
Jonty Horner, Professor of Astrophysics at the University of Southern Queensland. And if you've got time, jump on our website and have a look around. Maybe send your comments and thoughts to us via the Ask Me Anything button at the top. It's labelled AMA. And while you're there, check out the Astronomy Daily feed. Maybe sign up for your daily dose of astronomy news. Maybe you'd like to become a subscriber. You can do that. Visit the shop. Lots of goodies in our shop and plenty more, so check it out. And thanks to Hugh in the studio as always, because he does something which we one day might find out about. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.